All right. Hi, everyone. Good evening. My name is Jasmine Parmley, and on behalf of Harvard Bookstore, the Harvard University Division of Science, and the Harvard Library, I'm excited to introduce this event with Sean Carroll, presenting his new book, The Biggest Ideas in the Universe: Space, Time, and Motion. Thank you so much for joining us this super cold evening. Tonight's event is part of our Harvard Science Book Talk series, which works to bring the authors of recently published science literature to our Cambridge community and beyond. To learn more about this series and our other upcoming events, you can visit harvard.com and sign up for our email newsletter, or check out the page harvard.com/science for more information. Before we get started, I'm just going to go over a few housekeeping items. First, just a quick reminder to please silence your cell phone for the talk. Tonight's event will conclude with some time for your questions. Just raise your hand during the Q&A portion, and one of our event staff will bring you a microphone. And just to note that C-SPAN Book TV is here recording this event today, and they will be recording audio from audience Q&A. If you haven't picked up a copy of The Biggest Ideas in the Universe yet, or if you would like your copy personalized, we will be moving to Cabot Library, just across the hallway, right after this event, for a signing and reception with some snacks. And thank you so much for buying books from Harvard Bookstore. Your purchases support our author series and help to ensure the future of our local independent bookstore. And thank you so much to our friends at Harvard for all of your help in making events like this one possible. Introducing Sean Carroll tonight is Cora Dvorkin, Associate Professor in Harvard's Physics Department. She is a theoretical cosmologist whose areas of research are the nature of dark matter, neutrinos and other light relics, and the physics of the early universe. Please join me in welcoming Cora Dvorkin.
It is an honor for me to introduce Professor Sean Carroll today. Sean Carroll has recently become a Homewood Professor of Natural Philosophy at Johns Hopkins University, and he's also a faculty at the Santa Fe Institute. He's a theoretical physicist, and as such, he has written many interesting research papers. He's also a popular science writer and has been a New York Times best-selling author. I always find him very insightful and thought-provoking. I read his book in General Relativity when I was an undergrad in Argentina, and ever since then I became fascinated with the topic. He's very committed to making complex physics ideas accessible to everyone, and he does it in a very unique and wise way. So today he will be telling us about the first book in his new trilogy, The Biggest Ideas in the Universe: Space, Time, and Motion, where he explains not only the physical concepts, but also the mathematical framework behind them in a very beautiful way. So please join me in welcoming Professor Sean Carroll.
Thank you, Cora. Thank you, Harvard Bookstore, one of my favorite bookstores in the whole world. Thank you, Harvard University, one of my favorite universities in the whole world, where I got my own PhD here a certain number of years ago that I will no longer admit in public. And thank you all very much. I realize it's a little chilly out there. I am very happy that you were able to brave the elements to get here. And as mentioned, we have, I wonder if this is a laser pointer. What do you think? Is there something I can push on it? I'm a little afraid. Oh yeah, look at that. I've written a book, The Biggest Ideas in the Universe, Volume 1. Volume 2 will be about quantum mechanics and field theory. Volume 3 about complexity and emergence. But there are too many big ideas in the book to talk about all of them, so I figured I would pick a big idea and I would talk about that to give you a flavor of what you would get were you to buy the book. And so the thing I wanted to talk about was Einstein's equation. And you know, as soon as I say that, you're thinking, well, okay, I've seen that before, good, this is familiar territory, E equals mc squared, energy, mass, speed of light squared, good, I'll learn something maybe, but it's not going to be completely unfamiliar. But this is not Einstein's equation. This is not what a physicist would mean if they said, oh yes, I was thinking about Einstein's equation earlier today. Here is Einstein's equation. As a physicist thinks about it. Were you to say it out loud, it would be r mu nu minus 1/2 r g mu nu equals 8 pi g t mu nu. This is the field equation for the curvature of space-time itself in general relativity. And we never tell you about this. We might give you the words. We might say space-time is curved and that curvature is gravity, things like that. But we don't give you the equation unless you're a physics major. Shout out to those physics majors in here. Maybe you'll get it. But even then, most undergraduates never see this equation if they get a physics degree. It's considered to be too hard. There's all these Greek letters in there. There's subscripts. We don't know what's going on. An hour from now, you will all know what's going on. I'm going to teach you this equation. So how do we get there? Well, we start with classical mechanics. The whole theme of book 1 is classical mechanics as opposed to quantum mechanics. And classical mechanics, the central equation there is Newton's second law, F equals ma. My physics teacher, when I was a freshman, said that, the only equation you need to remember for the test is F equals ma. You can derive everything else. That's an exaggeration, but that tells you the central importance of this equation. Force is mass times acceleration. Why is this equation so interesting and important? In part because it's precise. In other words, it's not just a suggestion. This is the difference between equations and words. It's not just saying the more you push, the more the object will accelerate. It's a very precise quantitative relationship that you can use to fly a rocket to the moon. That's the kind of precision that you need. But the other thing that we don't always appreciate is that it's universal. What I mean by that is, it's not just saying, this one time I pushed a car with a certain force and it accelerated by a certain amount. It's saying every time, everywhere in the universe that a force is exerted on an object with mass m, you can use this equation to figure out how it will move, how much it will accelerate. Now, were this a philosophy lecture rather than a physics lecture, we would ask, why are there relations in the universe that are that precise and that universal? Happily, we're lower brow than that today. We're physicists. We notice that there are, we celebrate that, and we move on. So we want to learn how to use this equation, right? F equals ma. If you exert a force on something, it will accelerate proportional to its mass. But you need to know what the force is. So Newton himself talked about a famous force, the force of gravity, Newton's famous inverse square law. So if you have a little object with mass little m, this is the one that is being forced on and will start accelerating. So this might be the Earth. And a bigger object with mass capital M might be the sun, okay? And you can ask how much force is exerted by the force of gravity. And Newton says if you have capital M for the big object, little m for the little one, I remember I can also use my computer for this. Look, there's little m. You draw a little vector, okay? A little thing with magnitude and direction. And if you see a vector labeled E, it will often be what's called a unit vector, a vector with a fixed length that doesn't change its length under different circumstances. And what we're asking is, F, what is that vector? What is the force that is acting on this object with mass little m? So really, this equation, because of the little arrows on top of the F and the E, this is an equation not just between two numbers, but between two columns of numbers. F, the vector, has a certain amount of force in the x direction, a certain amount in the y direction, a certain amount in the z direction. That's what it means to be a vector. It has both a size and also a direction it's pointing in. And the direction it's pointing in this case, is that the force is along that unit vector pointing from the little mass to the big one. And the size of it is big M times little m times capital G, which is Newton's constant of gravitation, divided by the distance squared. That's why it's the inverse square law. When you're very close to objects to each other, the gravitational pull is relatively strong. When they're far away, it's relatively weak. And this is how it goes. And so what a physicist would do is to start with some setup. Here are two objects, here are their masses, here's their distance, here's how they're moving. What happens next? How do they move next? And there's a very nice simplification that occurs right away, that the mass of the object being pulled cancels out. Okay, so F equals ma, but F also equals gmm over r squared times E, and so by math, you can divide by little m on both sides of that equation. And what you get is an equation for how much the little object is being accelerated by the force of gravity. And what you notice is, nowhere in the equation are any actual individual characteristics of that object. It doesn't matter what it's made of. It doesn't matter how massive it is, or how fast it's spinning, or what day of the week it is. Every object, the same distance from some other object, will accelerate in the same way. So you can do this experimentally. You can go up to the moon. So here on Earth, if you drop a hammer and a feather, they won't fall at the same rate, but that's because of air resistance, not because of the laws of physics at some deep level. If you go up to the moon where there's no air resistance, you can ask, if I drop a hammer and a feather, will they fall at the same rate? And this was done by the Apollo 15 astronauts. Hopefully they already had some faith in Newton's laws of physics, because otherwise they would not have gotten to the moon to do the experiment, but happily it turned out right. They made very grainy videos, so this is an artist's reconstruction of the event, but two objects, even with very different masses, fall in the same way under the force of gravity. Now that is not just acute coincidence. This is going to turn into the single most important fact about gravity. Gravity is universal. It doesn't matter who you are or what you're made of. We all accelerate under gravity in the same way. That's going to be crucially important. Why? Because as successful as this paradigm was, this whole setup that Isaac Newton gave us for doing classical mechanics, it was not the final word. In 1905, we had input from this guy, Albert Einstein. You know, these days when you see a picture of Einstein, it's almost always in his later years, right? He was a little rumpled, the sweaters and everything, and you get the impression that's what physicists are like. This is what Einstein looked like when he was deriving the equations of special relativity and general relativity. His hair was combed, someone was dressing him nicely. I don't want to say what the causal relationship there is, but he was a sharp-dressed young man. That's all I'm going to say. And the theory of special relativity, 1905, is contrasted with the theory of general relativity. In special relativity, there's no gravity. In general relativity, there is. We will get to that. But what Einstein did in 1905 was he didn't really invent the theory of special relativity out of whole cloth. There were already various lines of reasoning that were coming into it, and he really put it all together once and for all. And we're not going to go into details about special relativity, but you've heard some of the jargon, some of the phrases, right? Motion is relative. That's where the word relativity comes from. The speed of light is constant. You can't go faster than the speed of light. It's an upper limit. And then there's all these phenomena that you're taught about, length contraction, time dilation. In the book, I don't emphasize these things that much, because in my quirky idiosyncratic worldview, focusing on things like length contraction is a remnant of the fact that back in the Newtonian days, there was something called length, and everyone agreed on what it was. And it turns out in the relativity picture, different people are not going to agree on what length is. So rather than starting with length and saying, but it contracts for some people and not for others, I try to start with what is actually true and correct in the theory of relativity and derive everything from that. But all we need to know right now is that Einstein didn't actually, even in 1905, put the finishing touches on the theory of relativity. That was done, arguably, 2 years later by Hermann Minkowski, who used to be Einstein's professor. So Minkowski was a mathematician, not a physicist, but he was proudly following his students' progress. He knew about the theory of relativity. And it was he who first said, all of this great work in your theory that you've done, Albert, can be simplified and conceptually made more clear if you just say that space and time are not separate. Space and time are together unified in something called spacetime, and all of these effects that you're talking about are manifestations of the geometry of spacetime. And his famous quote is, "Space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." No way that referees would let him get away with rhetoric like this in a physics paper today, but 100 years ago you could do it. Not everyone was impressed by this mathematical step forward, including someone named Albert Einstein, who wrote in one of his papers that Minkowski's formulation makes rather great demands on the reader in its mathematical aspects. So look, Einstein, let me go out on a limb here, was no dummy. But he famously only did as much math as he absolutely had to do. He was good at math, but he was a physicist at heart. He didn't do math for the sake of doing math, and he constantly resisted people who tried to take these physics theories and just turn them into math for its own sake. And he was worried that that's exactly what Minkowski was doing. Turns out he was wrong, and one of Einstein's, maybe his single most important feature, was his ability to be wrong and then change his mind. He would very quickly change his mind and jump on the bandwagon, and he came to believe that the space-time way of thinking about relativity was actually the right way to think about it. So let me tell you what that way is. The question is, why is it geometry that we should be thinking about when we're thinking about relativity? If you read all the popular level expositions of length contraction, etc., you don't really hear the word geometry that much. But the essence of it is this. When you want to travel a certain distance in space, there's a formula that relates the amount of distance you travel to what we call the coordinates. Okay? This doesn't work in Boston, but in a sensible city like New York, where the streets are at right angles, you could figure out the total interval, the total distance between 2 points you go by taking the different sides of a right triangle, squaring them, and using Pythagoras' theorem, right? In this little triangle here, d squared equals x squared plus y squared. So what this means is, number one, you have a formula for figuring out the distance between 2 points in terms of their coordinates, but also this is something you could measure, and you notice there's a difference between how much distance you would travel depending on the path you take. This is a point that is so obvious it's almost not worth saying, but you can have 2 points a certain distance apart, and everyone agrees what the distance is. But walking a straight line between those 2 points means that you personally travel less distance than if you go off on a detour and then come back. Right? Again, perfectly obvious. The distance you travel between 2 points depends on your path. The reason why I am emphasizing this perfectly obvious point is because the whole point of relativity is that the same thing is true, but for time rather than space. Time, like distance, is something that will, the elapsed amount of it, depend on your path through the universe. And it's Minkowski that gives us a formula for figuring this out. If you travel some distance in space, and there is some time coordinate on the universe, right? Like there's some universal time that everyone agrees on, that the International Bureau of Standards has set up, so there are clocks everywhere, and we can read them and figure out what it is. In relativity, that universal time coordinate is not the same as the time that elapses on your watch. The time that elapses on your watch is something that you personally experience, and Minkowski's point is that time is like space. The amount of time you experience will depend on how you travel through the universe, in exactly the same way that the amount of space that you travel through depends on the path you take. And here is the formula. It's kind of like Pythagoras' theorem, but it's not exactly the same. Tau, the Greek letter tau, stands for what we call the proper time, the elapsed time, the actual amount of time you experience, okay? And there's a formula for it, t squared minus x squared. I've sneakily set the speed of light equal to 1. So you don't see the speed of light in here. There's a certain fraction of you that are doing dimensional analysis in your head and wondering how I can subtract time from space. So cavalierly, the answer is we're using units where length is measured in light years and time is measured in years. Okay? So the speed of light plays a special role in this theory. But the real point here is that the time that you will feel elapsing is given by this formula, and for a given change in the coordinate time t, it will depend on your path through the universe, how much time you actually experience, with a twist, right? Because in space, we all know the shortest distance between 2 points is a straight line. And you can figure that out. If you, rather than going on this angle here, if you just gone straight up, you would experience less distance. But here, it's not x squared plus t squared, it's t squared minus x squared. This is saying that the more you move out in space, the less time elapses on your watch. So the rule in relativity is not the shortest distance is a straight line, but the longest time is a straight line. The more space you traverse and come back, the less time you will experience. So you've heard of the twin paradox, where there's two twins, one zooms out near the speed of light and then comes back. It's always hard to remember which one experiences more time. The one that moves fast and then comes back always experiences less time, because the longest time path is the one that just stays stationary. There you go. So this is geometry, right? This is Pythagoras' theorem that we've updated for the space-time outlook. And there's a minus sign in there. That minus sign will turn out to be important, but it's still kind of reminiscent of things that we've seen in our good old high school geometry classes. Why do we care about this? Well, remember this guy, Einstein, he wasn't done yet in 1905. He had established special relativity. But remember, the first thing that Newton did when he had established classical mechanics, special relativity was an update of the rules of classical mechanics. But you still want to say, like, what are the forces? What is it that's pushing you around? And the very first thing Newton did was gravity. Now, in the case of relativity, a lot of the equations of relativity were inspired by electromagnetism, and electromagnetism fit in with relativity very, very well right from the start, but gravity hadn't gone away. So what Einstein wanted to do was to update Newton's law of gravity to reconcile it with the new rules of relativity. This turns out to be harder than you think. There's a certain set of obvious guesses that you make. They don't work. Einstein was no dummy. He put his noodle to work at this. He was distracted by things like quantum mechanics. That got in the way. But eventually, he really focused in on how can we reconcile relativity and Newtonian gravity. Remember that fact that we learned about gravity, that it's universal. That was the key to unlocking the puzzle that Einstein had set himself. And he called it his happiest moment of his life, where he realized this following very mundane fact. If you're in a sealed room like we're in right now, we feel the force of gravity, right? For me, it's pushing up on my feet. For you, if you're sitting down, it's pushing you up, preventing you from falling to the center of the earth. We can feel that there's gravity. Clearly, there's gravity, right? But Einstein says, what if the earth wasn't there, but instead, the whole science center is on a rocket, and the rocket is accelerating at 1g with a very, very quiet rocket engine? He claims you wouldn't be able to tell. Because, of course, an accelerating rocket would also feel like it is pushing you up, just like the Earth does in the force of gravity. And, you can say, well, what about other forces? What's so special about gravity? If there was an electric field in this room, you could easily measure the electric field. Because you take an electron, which is negatively charged, it would be pushed in one direction. Proton, positively charged, pushed in the opposite direction. But remember, we just learned in a gravitational field, everything falls the same way. Einstein realized that's exactly the same thing that would be true on the rocket. Everything would fall the same way. So if you're in a small region of the universe, not able to look at the outside world, you can't tell whether you're in a gravitational field at all. You could mimic all of the effects of gravity by just accelerating in a small enough region of space-time. You or I would come up with that insight. We would pat ourselves on the back, then go have some pizza or something. Einstein was not done yet, because he was trying to think how to reconcile gravity with relativity, and he realized that if gravity is universal, if it has this special feature that you can't know that it's there in the room, that means that gravity in some sense isn't a force like the other forces of nature, like electromagnetism. It's an intrinsic feature of space-time itself. What feature is it? It is the geometry, the curvature of space-time. He knew about Minkowski's work. He begrudgingly began to think that maybe this was a good idea. In Minkowski's geometry, there's a minus sign in Pythagoras' theorem, but it's still flat geometry. It's still in some sense like the Euclidean geometry we learn in high school. What Einstein posited was that when we feel gravity, it's because you need to generalize that flat geometry to curved geometry. Maybe, he said, the force of gravity is a manifestation of the curvature of the geometry of spacetime. The problem was Einstein knew nothing about the geometry of curved surfaces and higher dimensional spaces. He didn't know the right math. Again, he didn't learn math until he was forced to do it. But he was forced to do it under these circumstances, and happily he once again had a friend. He had a buddy, Marcel Grossmann, who was a college classmate of his who had become a professional mathematician. So Einstein was tutored by Marcel Grossmann on the differential geometry of curved spaces, which was only invented in the mid-19th century. It wasn't that old at the time. And so we owe a debt of gratitude to Marcel Grossmann for teaching Einstein about curved geometries. There's literally a famous general relativity meeting that happens every 3 years called the Marcel Grossmann meeting in his honor. So here's Marcel Grossmann next to Einstein. Einstein's sitting there as if he's a student again, learning the mathematics of curved spacetime. So what is that? I know you're desperate to know. What is the mathematics of curved spacetime? There's a story that you might have heard about the invention of non-Euclidean geometry. So there's Euclidean geometry, which is what we learn in high school. It is associated with things like Pythagoras' theorem, the area of a circle is pi r squared, and most famously, the parallel postulate, or most infamously. What Euclid did back in the day when he really systematized the study of geometry, most of the results that we know about from Euclidean geometry, other people had already derived. What Euclid did was to systematize it by saying, here's a set of axioms from which we can prove all these other results. And there was always one axiom that kind of stuck out as annoying. Like most of the axioms were pretty indisputable, but there was one called the parallel postulate that said the following thing. If I take a little line segment, and from that line segment, I take two other line segments shooting out at right angles. Okay, so here we are, little tiny line segment, two other line segments going at right angles. Follow them forever, says Euclid. And he says no matter how far you follow them, they will stay at exactly the same distance from each other. That is the parallel postulate. And it makes a certain amount of sense. That's what parallel kind of means, right? So it took until the 1830s for people to say, well, what if it didn't? What if two initially parallel lines didn't remain parallel? And what they realized was you could invent alternatives to Euclidean geometry. This was a surprise because people thought that Euclidean geometry was the unique thing to do. But it turns out if instead of saying those initially parallel lines always remain the same distance apart, you could say, well, what if they come together? You derive an entirely new kind of geometry called spherical geometry, or what we would now call positively curved geometry. And if instead you say, what if the initially parallel lines diverge with time, you get negatively curved geometry like a Pringle or a saddle or something like that, okay? So these are different ways, and it's not that surprising. You've all heard of spheres, right? There's a sphere, I can draw a triangle on it. If I draw a triangle on a flat plane, the angles inside add up to 180 degrees every single time. If I draw a triangle on a sphere, the angles inside will add up to more than 180 degrees every single time. And if I draw a triangle on a Pringle, I don't know how you do that, but the angles inside would always be less than 180 degrees. So there's a systematic set of choices you can make. And this was very, very exciting in the 1830s, and people said, great, there are three different kinds of geometry. The problem is, it's not a problem, but there's a hidden thing going on here as well. All three of these choices are very, very special. Because if you've ever made a sphere out of clay or whatever, your sphere, you might notice, is not perfectly spherical. The Earth is not perfectly spherical. It's a little oblate. There are mountains, right? We can have surfaces or higher dimensional things that are kind of lumpy. Maybe it's positively curved in some places and negatively curved in other places. None of these choices was equipped to handle that. So there's an obvious open question. How do you mathematically describe surfaces and spaces where the curvature can be anything? Where it can be something in some direction, something at another place, etc. So people put their minds to that. One of the people who did it was Carl Friedrich Gauss, arguably the greatest mathematician of all time. He made some progress, but he kind of got bored with it. He had a graduate student named Bernard Riemann. And Riemann, I shouldn't say graduate student, Riemann had already gotten his doctorate degree, but the Germans, bless their hearts, the doctorate degree isn't enough. If you want to teach in a university, you got to get another exam after the doctorate degree. So Riemann went to Gauss, his advisor, and he actually gave Gauss a list of, here's what I might do my, what is called the habilitation degree on. And Riemann was already an extremely accomplished mathematician. You might hear about Riemann's surfaces. He did a lot of work in complex analysis. And Gauss looked at Riemann's list, and he pointed to the one that Riemann thought was the most boring, namely the foundations of geometry. But he was a dutiful student, he wanted to teach, and he went off to do it. And you can read his paper. No one ever reads these papers, right? It's worth looking at the paper. It's short, it's mostly words, and in it he kind of complains that he has to do this. He's like, yeah, this isn't really what I'm good at, but I was told to do this by my advisor. And the problem he is faced with is, what is the most absolutely general, arbitrary, powerful way to describe the geometry of not just the two-dimensional surface, but a three-dimensional space, or even hypothetical 28-dimensional things that we could invent? And the question is, when you have something that is arbitrarily curved, that seems like very hard to capture in an equation or in an expression. How do you take the information of what the geometry is and encode it in some data? And the answer that Riemann came up with, and this is why he was very smart, is if I draw a curve in an arbitrary geometry and I have a formula that will tell me the length of every possible curve I can draw, that will fix the geometry once and for all. And this is a dramatic thing, because you can imagine if you have some curved surface and you know its geometry, and someone draws a curve on it, you can calculate the length of the curve. We know how to do that. But Riemann says we can also go the other way. Knowing the length of every possible curve uniquely fixes the geometry of the surface or the space or whatever. And we know how to do that. It's going to involve something called calculus, and it's going to involve a generalization, once again, of Pythagoras' theorem. So Riemann's strategy was, if you want to calculate the length of a curve, you zoom in, and you calculate the length of an infinitesimal segment of the curve, and then you add them all up using calculus, okay? So what you want to do this is some generalization or equivalent of Pythagoras' theorem. Pythagoras' theorem is, here's the length of a straight line in Euclidean geometry. The distance squared is x squared plus y squared plus z squared. It's very much like what Minkowski gave us for spacetime. The proper time squared is t squared minus x squared minus y squared minus z squared. Those minus signs are in front of the spatial part, okay? So if you stare at these formulas for just a second, you will discern a pattern. On the left, there is some kind of interval squared, a distance or a time, right? On the right, there's a bunch of coordinates, x, y, z, t, and they are squared, but they're also multiplied by a number, either plus 1 or minus 1. So what is the most general version of these formulas? What is the general big picture concept that would include both of these formulas? Well, for one thing, we can include the possibility that it's not just x squared plus y squared plus z squared, but maybe there's x times y, x times z, something like that, right? The point is, on the right-hand side, the pattern is we have some kind of interval squared equals some number times one coordinate times the other coordinate. That is the pattern. So the most general formula, says Riemann, for the interval squared is some number times t squared. If we're doing space-time, so we have coordinates t, x, y, z. There's a t squared term, a t times x term, a t times y, a t times z, x times t, x squared, etc. Right? It goes on. How many terms? 16. 4 times 4 if you're in four-dimensional space-time, like we are, because there's one for each combination of one coordinate and another. And in principle, says Riemann, these coefficients, capital A, capital B, capital C, they could even change from place to place, because remember, we're allowing this curvature to be wild and crazy and unpredictable from point to point. So this is Riemann's answer to the question, how do we encode the geometry of a space? He says if we know what this formula is, at every point in the space, we know everything there is to know, or we can figure out everything there is to know about the geometry. This is true, and it's great. It's also a little clunky. Capital A, capital B, 16 of these letters, right? So what mathematicians are super good at is inventing slick notation. So let's invent some slick notation. Rather than writing T, X, Y, Z for coordinates on spacetime, we're going to call it X0, X1, X2, and X3, where these are superscripts now, not subscripts. Already the mathematicians are trusting that you have your wits about you, so this is not x to the 0 power, x to the first power, x squared, x cubed, okay? These are 4 different coordinates with labels, superscript indices. Why does time get labeled x0? Because sometimes we're in 3-dimensional space-time, sometimes in 10-dimensional space-time. It would get very annoying if we had to change the number on the time coordinate every time we change the number of dimensions. So, like computer programmers who start counting at 0, space-time physicists call x0 the time coordinate. And then they call the whole collection of 4 coordinates x mu, where mu is the Greek letter mu. So x mu means either x0 time x1 x, x2 y, or x3 z, depending on the value of mu, okay? You begin to see the origin of those letters that appeared in Einstein's equation when we started, r, mu, nu, etc. Those subscripts, mu and nu, stand for directions in spacetime, t, x, y, or z. And then, if you buy that way of writing down our spacetime coordinates, there's a very slick way of characterizing this interval, which we call the metric tensor. And it is written g mu nu, and what that means is, rather than writing a times t squared plus b times tx, etc., we say t squared is x0 squared, or x0 x0. So whatever's multiplying that, we're going to call it g00. G00 is the thing that multiplies x0, x0. G01 is the thing that multiplies x0, x1, i.e. tx. And likewise, all the g mu nus, there are 16 of them. G mu for mu going 0, 1, 2, 3. Nu for nu going 0, 1, 2, 3. So we have compactly written all of the information you need to convey the geometry of an arbitrary space in an arbitrary number of dimensions. In 4 dimensions, like space-time is 4-dimensional, g mu nu will be 4 times 4 components. You can imagine a 100-dimensional space, and then g mu nu would be 100 by 100. But still, you just write g mu nu. That's why the notation is slick, okay? Good, that's enough math. Let's get back onto physics. Let's recover what Minkowski was saying, but now in this slick new language. So remember, Minkowski said that the time you experience on your watch obeys this formula. Tau squared, that proper time, is t squared minus x squared minus y squared minus z squared. So in our new notation, there's a coefficient of t squared, that's x0 squared, and the coefficient is 1. So G00, or GTT if you like, is 1. Whereas the coefficient of x squared, which is GXX, or G11, is minus 1. There's also a coefficient of t times x, but there is no t times x, so that coefficient is 0. So the whole shebang is a matrix, a 4 by 4 array of numbers, which in this case just have non-zero entries on the diagonal, okay? And we can actually associate all 16 of these numbers with some meaning. They mean something. They're not just arbitrary symbols. All of the parts of g mu nu, which have 2 space indices rather than a time index, so like gxx, gxy, etc., those tell us the spatial distances. These are telling us literally the distance along some curve that you could draw. Whereas gtt is telling us, if this makes any sense, how fast time is flowing, Really what it's saying is, how fast is your proper time changing with respect to some background coordinate time, t? And then there's this weird new possibility, and this is one of the reasons why math is fun, because just by thinking of ways to generalize something we already know, we open ourselves up to new possibilities. So if there were non-zero parts of the metric, which were involving both time and space, so like g, tx, ty, tz, that would represent time and space twisting into each other. I don't know about you, but as I go through my everyday life, time and space do not often twist into each other, so I don't need to worry about this, which is why people didn't worry about this for a very long time. But it turns out the universe worries about this a lot. Time and space twist into each other very dramatically in this picture. Anyone recognize this picture? This is from Interstellar, the movie, directed by Christopher Nolan, but the original idea for the screenplay came from Kip Thorne, a physicist and Nobel laureate at Caltech. This is a giant spinning black hole. This is in fact a computer image. It is not data from a telescope. It is a computer simulation of what it would look like if the light from the gas around the black hole spun around the black hole before you could see it, okay? And this was, when they made it, they worked very hard. The Hollywood budget is larger than the Caltech budget, let's put it that way. So they were able to devote quite a bit of computational resources and thinking into making the most accurate image of a black hole that they could imagine making. And Kip collaborated with people from the special effects shop, and they wrote a paper that appeared in the journal Classical and Quantum Gravity on visualizing the gravitational lensing by a spinning black hole. And crucial to making this work is the idea that time and space twist into each other when the black hole is spinning like that. So these things turn out to matter, and will matter more whenever we visit a spinning black hole. Okay, there's one final piece of math that we need. We said that what we have is a space or space-time with arbitrary amounts of curvature. We can capture the geometry of that manifold, as we call it, or space, in terms of the metric tensor. But the metric tensor also depends on the coordinate system we use, right? Polar coordinates, Cartesian coordinates, whatever. What we want is not something that is just telling us what coordinate system we use, but rather something that right away tells us what is the curvature of this geometry that we're looking at. So guess what? We have to work a little bit harder. The answer is something that is properly called the Riemann tensor, named after Riemann, r lambda rho mu nu, for example. It is something that you can construct from the metric. So it's not a whole new thing. Riemann was right. Once you have the metric, you can calculate whatever you want. One of the things you can calculate is the Riemann tensor, which tells you how curved space-time is. And the way it tells you that is by telling you exactly how Euclid's parallel postulate fails to be true, okay? So what Euclid says is, here's a little straight line segment at some point in space or space-time. We pick a direction from which we send out two rays, and we let them go, and we ask how they change. And what Euclid postulated was they stay exactly the same distance apart. What the 19th century geometers said is not necessarily. And what Riemann said is, in particular, they could twist around, they could expand, they could contract, they can do all sorts of things. So we have a very complicated question we're asking. For any point, starting with any line segment, pointing out two initially parallel lines in any direction, how do they twist or grow together or come apart? The answer is given by the Riemann tensor. So you tell me what initial line segment you have, what direction you're shooting out new rays in. The Riemann tensor will tell me how they come together, push apart, twist around each other, etc. It's a little black box that does that for you. At every point in space-time, it tells you exactly how wrong the parallel postulate is. Now I know the first thing that hits you when you see the Riemann tensor, r lambda rho mu nu, is that's a lot of Greek letters. Like you were with me when we had G mu nu, that was only 2 Greek letters. And that was like a matrix, a little square array of numbers. What in the world does it mean when we have 4 Greek letters hanging around our object? So what it means is when you have a vector, which you can have a vector in space-time, like the momentum vector of a particle, that is a vector. It has one index telling you what direction in space-time a certain component is indicating. So we might call it p mu. That's a vector. There's 4 components, pt, px, py, pz, okay? The metric tensor, a little souped up compared to that, it is 4 by 4. So there's 16 different components. The Riemann tensor, r lambda rho mu nu, is 4 by 4 by 4 by 4. It is a 4 by 4 matrix of 4 by 4 matrices. I've written them out. There you go. Please do not find a typo in the slide. Don't even pretend that you found it. And if you have, don't tell me. Writing this down is purely showing off. This is completely useless. This is why we invent the slick notation, where we can just write r lambda mu rho, r lambda rho mu nu, okay? It's a lot of components, 256 numbers, but they're all there implicitly in the metric. So we can calculate them. And these numbers, even though it's a lot of them, there's a finite number and they tell us how curved the space is that we're in. So to catch our breath, here's where we got. We're considering the possibility that the geometry of space-time can be arbitrarily complicated. It can be flat in some places, positively curved in some directions, whatever you want. Riemann teaches us that we can characterize that if we know how to calculate the length of every little infinitesimal line segment. The information we need to do that is captured in the metric tensor, G mu nu, and the curvature of that metric tensor is captured in the Riemann tensor, r lambda rho mu nu. Okay? That's what Einstein had to learn. It only took you like 20 minutes. It took him years. Okay? So congratulate yourselves. There are some details that I've been hiding from you, but I did write a book, and you can buy the book, and the details are in the book. But what Einstein wanted to do was to take all this math and finally use it to accomplish his task of generalizing gravity to curved space-time. He wanted to get an equation for gravity that would replace Newton's equation. This is Newton's equation for the acceleration of an object in a gravitational field at a distance r from an object with mass capital M. So you need to replace both the right-hand side and the left-hand side. On the left-hand side, you have acceleration. What you want to replace that with, one guesses, is some measure of curvature of space-time. On the right-hand side, you have capital M, the mass, the thing that is causing the gravitational field. So you want to replace that with some relativity version of mass. M by itself is not going to be enough. You know that somehow in relativity, mass and energy kind of hang together. That's what E equals mc squared tells you. What is it in relativity that tells you everything you need to know about energy, mass, and so forth? The answer is, guess what? A tensor. It is the energy momentum tensor. T mu nu, so it is once again a 4 by 4 matrix of numbers, and all these numbers mean something. T00 or TTT tells you the energy of the object that you're looking at, and that includes the mass. So most of what matters is actually in that upper left-hand corner of the energy momentum tensor. But the other diagonal terms tell you the pressure. So if you have a gas, like in this room, there's a pressure in the x direction, y direction, z direction. There it is. Pressure is unified with mass and energy. And the off-diagonal terms tell you all this stuff about momentum and heat flow and stress. This is the great accomplishment of relativity, that things that you thought were separate are unified together. So the source of gravity for Newton is the mass of the object. The source of gravity for Einstein is everything energy-like about the object. The heat, the mass, the momentum, the pressure, all those things matter, and they're all captured in the energy momentum tensor. So, what do? Now we're playing physics, no more math for us. We have the metric, we can derive the Riemann tensor from it. We have mass that has been generalized into the energy momentum tensor, and our self-appointed task is to replace Newton's equation. A is gm over r squared times E. So somehow what we think we want is an equation relating the Riemann tensor, which we said characterizes the curvature of space-time, to the energy momentum tensor. There is a problem right away that the Riemann tensor is a 4 by 4 by 4 by 4 array, a 4-index tensor, whereas the energy momentum tensor is just a 4 by 4 array. They don't even have the same number of components. We cannot possibly just set them equal to each other or proportional or anything like that. We have to be a little bit more clever. Happily, there's a way to do this. We can take the Riemann tensor, and from it we can sort of boil it down to build smaller tensors that tell us some of the information about the curvature of space-time, but not all of it. There's one called the Ricci tensor that only has 2 indices. There's something called the curvature scalar that has no indices at all. Okay? So the point is these are well-formed geometric objects with fewer indices than the original Riemann tensor. And you look at that and you know in the back of your mind we want to set something equal or proportional to the energy momentum tensor, T mu nu. Your eyes are drawn to the middle one, the Ricci tensor, because it also has 2 indices. So it's the most natural thing in the world to guess that R mu nu, the Ricci tensor, is proportional to T mu nu. And if you guessed that, congratulations, you and Einstein both. That's what he guessed. Turns out not to work. It turns out that if that were the right answer, energy and momentum would not be conserved in the right way. So you have to be more clever than that. Einstein was, and you got to imagine him, 1915, sort of feverishly scribbling things down, because by that time, Einstein, bless his heart, he'd given like 20 talks on general relativity before he was finished formulating the theory. So everyone in Germany knew that this was the project to be worked on, and there were some brilliant mathematical minds working on it, so he had to work fast. And he succeeded. Here's the answer. You take the Ricci tensor and you subtract from it 1/2 times the curvature scalar times the metric. So those two things combined are still a 2-index tensor, a 4 by 4 array. You set those proportional to the energy momentum tensor and you get the right answer. That is what physicists think of as Einstein's equation. That is where we started. See, it was not so hard. But we're not done yet. I got to tell you one more thing, because what one does, of course, after one gets an equation like this, one has a drink or something, but how do we know whether it's the right equation? We have to do what is called solving the equation. In other words, this is an equation that, because remember, the Riemann tensor can be calculated from the metric tensor. So if you have a metric tensor, you can calculate R mu nu and then R, and you can ask, does it actually equal 8 pi g t mu nu? And so the solving of the equation is looking for functions that go into the metric tensor that would solve this equation. So we actually, I've been saying, waving my hands, the Riemann tensor can be calculated from the metric. What does that actually mean in practice? So here is one component of the Riemann tensor written out in terms of the metric tensor. When I was your age, we calculated this with pencil and paper. Kids today use computers to do it. They're really missing out on some fun late-night experiences when you wrote a mu when you wanted to write a nu, or a row that looked like a mu. But the point is, it can be done, and in fact, it's not as hard as it looks, because usually you're looking at situations where there's a lot of symmetry and things like that. But you know who looked at this and said, this is too hard? Albert Einstein. He said, look, I love my equation, it's very beautiful, nobody will ever solve it. It's too hard to solve it. How in the world could we ever solve this equation? Someone in the audience, when he said that, was Carl Schwarzschild, who was a German astronomer and physicist and mathematician who was serving in the German army at the time. But it was World War I, right, 1917. But you had some shore leave, and Schwarzschild decided to go to Einstein's lectures at the Berlin Academy during his leave. So he learned about general relativity, then he goes back to the front, And in his spare time, he says, I can solve this equation, and he gets this solution. What does it mean to get a solution to Einstein's equation? It means to get a form of the metric as a function of where you are, as a function of the coordinates in space-time. So the question that Schwarzschild asked was, what if I have an object like the sun, and I idealize it so that it's not spinning, it's not oblate, it's perfectly spherical, and around it it's just empty space. So everything is spherically symmetric and nothing is changing over time. That's a dramatic amount of simplification, and it allowed him to actually solve the equation exactly. This formula is what we now call the Schwarzschild metric. This is what you do in general relativity. You find metrics that solve Einstein's equations. You're finding a 4x4 array of functions of t, x, y, z, or in this case, because it's spherical symmetry, t, r, theta, phi, which are polar coordinates or spherical coordinates. And Schwarzschild was right, and Einstein immediately got it and was kind of chagrined that he had said it couldn't be done. He congratulated Schwarzschild, and Schwarzschild died the year later because he contracted a terrible disease at the front. There's a lot of people who went through things like that, but this is still the solution to Einstein's equation you would use to calculate the motion of the planets around the sun in the solar system, okay? So Schwarzschild didn't ask what happened inside the sun. That's actually harder. That's a little bit of work. You can do it. But he's just looking outside in empty space, okay? And so this is the right answer. It has been tested to exquisite precision. Einstein used it to predict things that were then shown to be correct. It was a wonderful success. But if you look at this closely, there's something weird going on. And physicists love to look at things closely, sometimes. So you notice that some of the terms in the upper left look like 1 minus 2gm over r. So what happens when r equals 2gm? Then that 0, 0 term here is 0. And this TT term, this RR term, is 1 divided by 0. You're not supposed to do that. That's infinity. That's bad. And furthermore, when r equals 0, this is infinity or negative infinity. That sounds worse. So if you plug in the numbers, you find that this is not an important problem for the motion of planets around the solar system, because this metric is only supposed to apply outside of the sun. And r is always much, much bigger than gm outside the sun, so this doesn't apply anymore inside the sun. But of course, your imagination is going to go, okay, what if we took the sun and we squeezed it down to a little ball so that it was smaller than 2gm? What would happen? The answer that would happen is a black hole. That point, r equals 2gm, is the event horizon of a black hole. And you can see this because remember the 0, 0 component of the metric, like all this pays off now. This is paying off. That 0, 0 component of the metric, which we said is the rate of time flowing compared to some coordinate, goes to 0 at r equals 2gm. And what that means is that if you throw a clock into a black hole, what you see is that it slows down more and more, and you never see it cross the event horizon. If you instead fall into a black hole, then your personal time just keeps ticking along, but you've made a terrible mistake. So the light from your cheeks is redshifted from the point of view of the outside observer, so it looks like you're very embarrassed that you have fallen into a black hole, which probably you are. This is an image, a slightly spruced up image from the Event Horizon Telescope, which many people here at Harvard have been working on as part of the Black Hole Initiative. The point I want to drive home is, Albert Einstein and Carroll Schwarzschild went to their graves not having any clue there was any such thing as a black hole. They weren't trying to understand black holes. They certainly weren't trying to predict their existence. What they did was derive an equation and then solve it. And the lesson is, the equations are much smarter than we are. This is why it's worth sitting through all this stuff about equations rather than just telling you stories and metaphors and analogies, because there's that precision and that universality in the equations. And then if you extrapolate them beyond what you were trying to understand originally, you might be surprised in very pleasant ways. The possibility of a black hole was lurking there inside Einstein's equation as soon as he had derived it, but it took decades for physicists to realize that is what the equations were telling them. These days, we use Einstein's equation to describe gravitational waves, the large-scale structure of the universe, in-spiraling black holes, the expansion of the universe itself, to find dark matter and dark energy. None of these things were on the mind of Albert Einstein in 1915, but they were all implicit in the equations. So as weird as they are, as much work as it is to look at them and go, I don't know, there's Greek letters, that's Greek to me, it's actually worth it to stretch our brains a little bit, understand these equations, because it lets us think about the universe in a very different and very important way. Thank you. And we are going to take questions. Maybe the house lights could come up a little bit, and there are people with microphones ready to respond if you raise your hand and have a question. And I'm supposed to call on them, but I can't see them, so...
That's okay. We'll take care of it for you.
Okay. Someone ask a question, and I'll answer it.
Hello, over here.
That doesn't help. Over here.
Oh, sorry. Back left side.
Stage
Here
left?
Yeah, stage left.
Okay.
Over here. Or stage right, left. I'm not sure. Up here. Your left. Hello, my name is Jason. Thank you for taking my question. Having all these tools to explain the fundamental workings of reality, what's next on your hunt, or what are your professional goals currently, besides grading papers at Johns Hopkins?
Well, not to be too obvious and cliched about it, but what drove Einstein to this great accomplishment was a fundamental incompatibility between gravity, as Newton understood it, and relativity that he had just invented. And we all know that there is a remaining, lurking, great incompatibility between Einstein's wonderful theory of general relativity and the theory of quantum mechanics. And we've been trying to reconcile these two things for a long time. Here is my wild guess. Quantum mechanics itself, which, by the way, will be the subject of Volume 2 of the biggest ideas in the universe, is something which physicists use all the time, but don't work very hard to understand. General relativity makes perfect sense. We know what it means. You got to learn it, but okay. It's very beautiful and very understandable. Quantum mechanics, we don't really know what we're saying when we talk about quantum mechanics in many ways. I think that the fact that we don't understand quantum mechanics might be related to the fact that we don't understand quantum gravity. I think that we got lucky when we made quantum theories of everything else in the universe, electromagnetism and the strong force and the fermions and so forth. Those were a simple step of starting with a classical theory and quantizing it. When you try to do that for gravity, for general relativity, it doesn't work. So my guess is we need to understand quantum mechanics better if we want to understand quantum gravity. Who's next? Yes. Anyone? Yeah.
Thank you. Thank you very much. Hi, I'm Steve. You touched upon the differences between physicists and mathematicians. And so in Riemann's paper, he hypothesized about the physical implications of his work. And in Einstein's time, Cartan got very close. And I'm wondering if you'd like to, take a victory lap about the physicists or Einstein getting to general relativity first, or what was it, in your opinion, that allowed Einstein to accomplish that when so others were, especially the mathematicians, very close?
Well, I do not want to take a victory lap. I appreciate the question, and I get it. But it's harder to find a better example of when you needed both mathematicians and physicists. The mathematicians would never have invented general relativity because they weren't being bugged by the incompatibility of Newtonian gravity and special relativity like the physicists were. But sometimes in the history of physics, they're faced with a new phenomenon and they need to invent new math. And physicists will sometimes do that. It would have taken a long time for the physicist to invent Riemannian geometry. That is something that you need to be an accomplished mathematician to do. So I think the right way to think about it is it was the perfect synergy between the physicist's way of thinking and the mathematical way of thinking.
How's it? Oh,
Go ahead.
hey there. So two of my take-homes. One, the equations are smarter than we are. I love that. Another one is that time is really weird.
Yeah.
So given those two take-home messages, you had a slide up there where you had a tensor, and there were a lot of other things that were being explained in the tensor that we didn't go into, which is totally fine. But I'm wondering if there's anything in those hidden dynamics about causation in terms of, empiricists are really trying to look at retrotemporal causal effects, but is there anything hidden in the equations, given that they're smarter than we are, that would indicate that, okay, causation is also not necessarily a linear type of effect that we might intuitively imagine it to be?
Good. So the short answer is no. I can elaborate a little bit. But I need to be careful because not everyone agrees with me, even though I'm right. This also frequently happens. I think that the notion of causation is not fundamental. I think the notion of causation emerges at a higher level of description where you have, among other things, a pronounced arrow of time that distinguishes between the past and the future. One of the most important things about cause and effect is the causes always come first in our macroscopic experience. And I think that you can account for that asymmetry in the same way that you account for other asymmetries in time via the increase of entropy and the second law of thermodynamics over time. But these equations that we're dealing with here are microscopic equations. They're not higher level coarse-grained equations. So they work exactly the same forward or backward in time, and there's no associated notion of causality. Stay tuned for book 3, where we will talk about this. Yes?
Hi, Professor Carroll. Thank you for this wonderful talk. You also have a wonderful podcast. I wanted to say that, okay, tonight we've learned that the geometry of space-time is pretty complex. And just as the previous audience member said, time is pretty weird as well. I wanted to ask, how should we get our heads around general knowledge statements such as the age of the universe is 13.8 billion years old?
Yeah.
What does that exactly mean given the weirdness of time and elapsed time considerations and the like?
Right. Very, very good question, because as we said, the amount of time that is elapsed depends on the trajectory that you take through the universe. We don't notice that in our everyday lives because it only becomes noticeable when two things are moving at relativistic speeds with respect to each other, near the speed of light. And so the point is that in the universe, in cosmology, the universe is full of things that are moving very slowly compared to the speed of light. Galaxies move with respect to each other at 1,000th the speed of light. And so when cosmologists say the universe is 13.8 billion years old, they mean from the perspective of just about any galaxy in the universe, that's the amount of time elapsed. We can imagine crazy galaxies that are moving near the speed of light that would have experienced a different amount of time, but there aren't any such galaxies, so we are a little casual about it, but there is something that is meaningful beneath it. Yeah?
Sean Carroll, thank you very much, and I'm a big fan. I watch your videos all the time. And as a result, I know that this might be a question that you might feel you can't answer. But Nima Arkani Hamed, he talks about the amplituhedron, and he does his talks, Space-Time is Doomed. Mm-hmm. And now I know from the Minkowski quote, that must be where he got it from, where space and time as separate ideas is doomed. So my question for you is, to the extent that you're familiar with his thinking, what do you think is the likelihood that he's onto something?
Nima Arkani Hamed, who was temporarily a Harvard professor for a little while, is one of the best physicists we have. The chances he's onto something are always very good. And I certainly agree with him that space-time is doomed. But that's the easy part. The hard part is what's going to replace it. And there, I don't know if his approach is on the right track or not. It certainly led to a lot of interesting things. I have my own approach, which was a little bit different, which is more immature, so we can't even say what it's leading to. But I do think that if we want to eventually get quantum mechanics as part of the fundamental understanding of space and time, space, at least space, maybe time, but at least space is not going to be fundamental. It's not that it's doomed, strictly speaking, but it's not going to be one of the fundamental ingredients in our story. It will emerge at a higher level. Space will be like the temperature of the air in this room. It's nowhere to be found in the fundamental laws, but it's a good concept to lean on at this higher level, coarse-grained level of description. I think that's quite likely.
Have there been any experiments to show how much parallel lines would deviate in space?
Yes, those are called gravitational lensing. That's exactly what gravitational lensing is. One of the first things Einstein realized is that light traveling through curved space-time would be deflected by the curvature of space. So you can watch initially parallel light beams come together. They don't go apart because gravity is attractive, but you can absolutely observe that. Likewise, in the cosmic microwave background, you can make a big triangle with us at one vertex and 2 points in the cosmic microwave background, the leftover radiation from the Big Bang, and you can add up the angles inside. And coincidentally, they do add up to 180 degrees because space is flat, but they could have been something else.
I've got a question from the world of philosophy, for what it's worth. At the beginning, you talked about universal laws, and you said philosophy would ask why a given law is universal, and so we won't worry about that. But I guess I think that a different way to frame that question, more fundamental way, is do we know that a given law is universal? If we don't know why, we obviously don't know that it's universal. And is that question worth examining?
So the question is, do we know whether a fundamental law is universal or not? I think that's a less interesting question because the answer is obviously no. We never know whether a law is universal or fundamental or not. We know it's the most fundamental we're currently working with, but that's the great thing about science is that tomorrow an experiment can always surprise us and change our minds. So there's never any claim here that we're done and we know that this is the most fundamental thing.
Was there anything interesting to you, or something that was predicted in the new James Webb telescope, like images?
Yeah, so the James Webb telescope, in my office at Johns Hopkins, I can look across the street and see the command center at the Space Telescope Science Institute, so I'm contractually obligated to say good things about it. But it's not hard, because it's a wonderful telescope that is absolutely teaching us new things about the universe. But let me say two things simultaneously. The JWST has already and will continue to teach us surprising and really important things about the universe and how it has evolved. And it is extremely unlikely it will teach us anything new about fundamental physics. That's not the kind of thing it's good at. It's good at seeing how galaxies formed and looking for planets around other stars and measuring their atmospheres and things like that. Super important things, but things that are absolutely within the realm of physics as we already understand it. So that's okay. Not every experiment needs to overthrow the laws of physics.
Let's take 3 more questions.
3 more questions.
Hello.
Better make them good.
Hello, my name's Ben. Just building on way up here on the left side.
Oh, there you are.
Just building on your comment on Interstellar and the attempt to make it quasi-realistic. Could you just reflect, and I'm sure you will in a future book, on the possibility of time travel and parallel universes? You just give me 30 seconds on what I'm sure is 1,000 pages of thought.
Sure, except I have to disappoint you. I'm not going to reflect on that because I reflected on it in a past book. So my very first trade book is called From Eternity to Here, The Quest for the Ultimate Theory of Time, and I talk about both parallel universes and time travel. The introduction of general relativity, which says that space-time is curved and dynamical, opens the possibility of thinking about time travel in a serious scientific way. My guess is that the answer is no, it is not possible. But honestly, we don't know, and that's kind of a thorn in our side. People like Kip Thorne and also myself have written papers about can you find solutions to Einstein's equation that would allow us to travel backward in time? And the answer is you can, strictly speaking, find them, but they always seem a bit pathological. There's no sort of clean, reliable way to twist space-time so much that you can go back and visit yourself in the past and undo your mistakes. Sorry. Yes?
Hi. Oh, that was loud. My name's Alex. Thanks for taking my question. Back when you were going through like the derivation of the equation that we were getting to in the end, we went from the 4-component Riemann tensor to the Ricci tensor. In doing this, aren't we losing, maybe my mathematical understanding of it isn't at a high enough level, but in doing this, aren't we losing some information, which would mean that we couldn't really do this? And if we aren't losing any information in doing this, why do we even write it out in the more complicated way?
Good. This is an excellent question. Someone's been paying attention. I'm very glad to see that. Yes, but think about it. So this equation right there in the middle, on the left-hand side, it involves some parts of the Riemann tensor, but not all of them. On the right-hand side, it sets it equal to the energy momentum tensor. So the fact that the left-hand side does not include the whole Riemann tensor allows us to imagine that if you have two spacetimes with exactly the same configuration of energy and momentum, you might have different curvatures of spacetime. And you do. And they're called gravitational waves. These gravitational waves can propagate in empty space. So one solution to Einstein's equation in empty space, so T mu nu is just zero everywhere. There's no stuff anywhere. One solution is Minkowski space, flat space-time, no curvature. But another solution is there's a gravitational wave going by. And so you don't want the left-hand side of Einstein's equation to absolutely fix the whole Riemann tensor in terms of the energy momentum tensor. You want to give it to some freedom. But it turns out you go the next layer and you do your math, the components of the Riemann tensor that are not directly fixed by this equation are nevertheless related to the components that are once you take their derivatives and things like that. So it's not that all hell is broken loose. There's still a way to derive the equations for gravitational waves from Einstein's equation.
Last question up at the top.
Hi there. I was wondering if you have a favorite current theologian or philosopher and why. And as you're thinking about trying to explain quantum theory or quantum mechanics, are there any philosophers or theologians that have helped you come to new ideas around the math equations or the physics that you're doing?
Well, technically speaking, I'm a philosopher, since I am jointly appointed in the physics department and the philosophy department. So my favorite one is myself. But if you exclude those, I'm not going to answer because the philosophers that I know and admire are all my friends or sometimes my enemies, and to pick out one of them would get them jealous. But let me instead of actually answering your question, let me say the following thing. There's a continuum of interest and research between strictly hardcore physicists who just calculate things and traditional philosophers who sit in their smoking jackets and talk about the meaning of life. Both of those poles of the spectrum exist, but there's a lot of activity in between. So we're starting up a new program at Johns Hopkins called the Forum on Natural Philosophy to bring back the good old days when there was not a dividing line between physics and philosophy or between science and philosophy more broadly. I think that there's plenty of science questions for which philosophy is completely irrelevant, but there's also plenty of science questions for which philosophy is extremely helpful, if not crucial. So rather than saying who is my favorite philosopher, I would rather say let's get everyone to be a little bit of a philosopher and a little bit of a scientist.
Thank you so much. That was great. Give him another round of applause. We're going to take the professor over to the Cabot Library for refreshments, and he's going to personalize your books if you want them personalized. They are all signed, and they're for sale in the lobby. Thank you, everyone.